Okay, now next up we want to answer the question of what is the bond order of molecular oxygen. So the bond order is something that we deduce from the molecular orbital diagram. And the equation is the number of bonding electrons minus the number of antibonding electrons all over 2. And the bond order is very, very useful for giving us chemical properties that can't necessarily, so the molecular orbital diagram is useful for calculating things like the bond order that would give us properties that we can't directly calculate, like the bond length, the bond strength / energy, and the magnetic properties. And so now we need to figure out how to draw the molecular orbital diagram of oxygen. So the molecular orbital diagram is generated by the combining of atomic orbitals. And so we have two types of combinations. We have constructive, which means you combine them when they're both in phase. And this is what makes our bonding molecular orbitals. And so this will form something like this, where you have a bit more density than before in between the two atoms. And that is what our bond is. Or we could have destructive addition, which is when you add them when they're out of phase. And what this does is it reduces the density, probability density between the two of them. And this is what gives us, this is bonding. And this one is anti-bonding. So additionally, because we have different types of atomic orbitals, we have different combinations with them. The general rule is that in order for them to successfully combine, they need to be similar in energy and symmetry. What this means is only atomic orbitals of the same level can combine into a molecular orbital, which means you can only get 2p combining with 2p, or so 2p combining with 2p, or 2s combining with 2s to form whatever it is. So because S is quite simple, you will only have the sigma bonding and the sigma antibonding, and this is just a general notation. And for P, we will have, again, two types of combinations. So we still have the bonding and antibonding, but they can combine in different ways because of the shape of the p orbital. So if we just draw out the shape of the p orbital, we know that we have 3. And so we have the on axis, and on axis will be the axis of combination. And so that would typically be the z-axis, and depending on the sign is when you'll get bonding or antibonding. So for example, these two are in phase, and so you'd get something that looks like that, and you can of course have out of phase additionally, but because of the remaining two p orbitals that are off axis, let's have something like this, and then you get antibonding, which would look something along the lines of that. And let's just have blue for our positive and red for our negative, and it would look something like that. And then again, also symmetry is very important when it comes to molecules. You would have different labels depending on the symmetry about the inversion axis. And so you have Gerard and ungerard, which are again just symmetry labels. These are important in cases like this where you have the same atoms combining, where symmetry is possible. And so Gerard means that the sign remains upon inversion. So like in this case, in the case of, so in this case, we would have Gerard. And in this case, it doesn't remain the same. It would flip, so it's ingrad. And so for the out of plane ones, we're gonna name them pi orbitals instead. So we'd have the y-axis and the z-axis, and both of them, of course, would also have their bonding and antibonding. So this is where the different levels of the molecular orbital diagram come from, because antibonding orbitals tend to have higher energy than bonding. Because of this out of phase relationship, there's going to be an increased repulsion here, and that's going to increase its energy. And that's about it. I'm just explaining the general things that you'll see in the molecular orbital diagram. So let's get to drawing it. Generally, energy will be going that way. Let's first draw out the atomic orbitals. We have O and O, and we're going to have O2 right here in the middle. So we have the typical 1s, and we're going to have a 1s antibonding and 1s bonding. Let's draw those in red after. For the antibonding, bonding, we have 2s. And remember, because they're s, we're only going to get 2 because we don't have anything that's out of plane. It's simply a spherical shape. And then lastly, we have the 2p. And this is where we get the out of plane combinations. And so we're going to have 2 here, and 1, and 2. Let's label them. Let's label the molecular ones too. So this is going to be our sigma for 1s, our antibonding sigma for 1s, our sigma for 2s, our antibonding sigma for 2s. The antibonding is just notated with that star. Next up, we have the pi 2p. So this is going to be the 2 off-axis ones that you see in the x and y planes. And then we have our sigma 2p. This is going to be the on-axis one in the z plane. Next, we have our pi 2p but antibonding and our sigma 2p but antibonding. And now we fill in the electrons. So we know oxygen has 8. So 2, 4, 6, 8, 4, 6, 8. Now we combine them. So we're going to get 2 here, 2 here, 2 here, 2 here. Next up, let's fill in the lowest one first. That took up 4. That leaves us with 4 more. And that is going to look something like that. Okay, so for our number of bonding, we have 2, 4, 6, 8, 10. For our number of antibonding, we have 2, 4, 6. So our bond order would be 10 minus 6 over 2. That's 4 over 2, and that is going to give us 2. So the higher the bond order equals the shorter the bond length. And if the bond length is shorter, that means they're closer together, which means there are more repulsive forces and just internuclear forces. And so we have a higher bond energy. And a really good way to just quickly gauge what your answer should be, you will have some scenarios where you do get a fraction, which you typically aren't presented with at the high school level. But in the case of oxygen, when we combine it, we get a double bond in between them and 2 electrons on each. That bond order of 2 is telling us that it's a double bond. If it was a bond order of 3, it would be a triple bond. So for example, this case, if we did the calculation, you get a bond order of 3. And that's about it for this question.